Well, we're going to start talking about graphing polar equations, and we begin with this little video that is going to be specifically about how we can graph some polar equations by converting to rectangular equations. But first, let's just kind of compare the two systems. We're used to graphing in rectangular coordinate systems, and we're used to the xy axis as we see here. Now, in the polar grid, many times we think of laying that on top of the xy axis, but really here we just have a polar axis, and that's all there is to it, a pole and a polar axis. And you'll notice in the background we see these concentric circles. This is really what polar graph paper would look like, and you can see why it's called polar equations, because that looks like we're looking down at the top of the Earth and we're seeing the lines of latitude and longitude, doesn't it? So it looks like we're looking down at the North Pole or maybe up from the South Pole. But in any case, the little lines that are radiating out of here represent a particular angle. This is 15 degrees, 30 degrees, 45, 60, 75 degrees, and 90, and so on. They're by 15-degree increments. And so it's very easy for us to, or we could use Radian Measure, of course. It's very easy to locate the concentric circles. Each circle, this is a one unit radius circle. This is a 2-unit radius circle. And so we can move along 1 unit, 2 units. That's easy to calculate that way. And we're not probably going to have polar graph paper to work with, but it's nice to kind of understand the bigger picture here. As I said, we're going to look at graphing polar equations by first converting to a rectangular equation, and that will enlighten us quite a bit on what these things look like. So here we've got a polar equation, r = 3, we're supposed to graph. And so we'd like to convert that to a rectangular equation, and we've seen how we could do this previously in an earlier section. We can be very clever, and what we'll end up doing here, as you recall, is we're going to square both sides. And when we square the left side, we get r squared. When we square the right side, we get 9. The reason we're squaring both sides is this way we've really created an r squared. That was the purpose. And r squared can be converted into x squared plus y squared from one of our pieces of information, conversion of polar to rectangular or vice versa. So now we have x squared plus y squared equal 9. We've converted it to rectangular equation, and we recognize that that is a circle that has a radius 3, and it's centered at the origin. We should recognize that from other work we've done in the past. And so when we go about graphing that, if we can think of this as the x-axis and the y-axis, then the origin would be here, which corresponds to the pole, and we have a radius of 3, 1, 2, 3. And so that's the circle that we're talking about. And the next example, we're to identify, and by the way, it kind of is giving us a hint right here, identifying and graphing a polar equation that's a line. Now, so here is our polar equation, theta equal pi/4. That is a polar equation. We need to convert that to a rectangular equation, which means that we need to somehow introduce x's and y's. And we remember that about the only equation relating x's and y's together is the tangent of theta is equal to y over x. But we don't have a tangent of theta, so we can create a tangent of theta if we take the tangent of both sides. And so that's the cleverness that we use here. We simply take the tangent of both sides of this equation. So on the left side, tangent of theta can be converted to y over x, which we knew. And tangent of pi over 4, we would just calculate. I mean, if this was tangent of pi over 6, or if it's tangent of pi, or some such thing, then we would just convert whatever that value is. Tangent of pi over 4 happens to be 1. And so now we have an equation that is y over x is equal to 1. And we can make that look better by multiplying both sides by x. And so this graph, theta is equal to pi over 4, is simply, in rectangular coordinates, the line y equal x. And we know what that line looks like, don't we? There's the line y equal x. Now, another way to have thought about this without converting is this equation has nothing to do with r. In other words, r can be any value. R can be 1, r can be -3, r can be 1/2, r can be 7.7, r can be -3.21, but as long as theta is equal to pi over 4. Well, the angle theta pi over 4 is right here, and so as long as we're along this angle, we can go positive or negative amounts since r can be anything. And so that makes a little bit of sense why we would have a graph that way. We could have, if we thought that way, we could have made the graph without this conversion. Let's see what we have next here. Oh, okay. Here we're going to graph a horizontal line. That last one happened to be a slanted line. And that's what's in store for us. So we're to identify and graph the equation r sine theta equal 2. Well, that would be hard for us to interpret like we could the last one. R equal 3 and theta equal pi over 4 are equations we could interpret without converting to rectangular coordinates. But this one's a little more, is less obvious. But when we recognize that r sine theta can be converted to just a y when we're dealing with polar coordinates versus rectangular coordinates, then we can replace the left side with y, and so we simply get the equation y equal 2. And of course the equation y equal 2 is a horizontal line. And it's the horizontal line that would be through the y value of 2. So if we looked up here, here's our y-axis, here's our x-axis, and y equal 2 would be 1 unit, 2 units, y equal 2, so here's that horizontal line. And there's just a little summary here about the circumstances when we can recognize that more generally. If we had r sine theta equal a, then of course that's y equal a, and so we would just have a particular horizontal line through whatever value a is, the y value of a. Now we can do something similar for vertical lines, and an equation of the type r cosine theta equal -3. Well, if we stop and think about it, r cosine theta can be converted to just an x. That's what we're doing, is we're converting rectangle. I mean, I can't look at that and say, oh, I know what that graph looks like. I know what it looks like because I can recognize that if I converted this to rectangular coordinates, I can replace r cosine theta with just an x. And so when I have x on this side equal -3, I recognize that as a vertical line. And it's the vertical line, whoops, it's the vertical line, there we go. It's the vertical line that goes through the x value -3. Well, here's the x-axis, here's the origin, if we're thinking in terms of rectangular coordinates. And so we'd go 3 units to the left to -3, and here we have that vertical line. And this is just another summary of that idea. Anything of this form, r cosine theta equal a, will be a particular vertical line through the x value of a, whatever that is. Whoops, wrong thing. Well, it's the wrong thing even more. Here we go. Now, once again, we're going to convert to rectangular equation of terms so that we can recognize what the equation would look like. And of course, there's a hint here that this is going to be a circle. We had one before, r equal 3, which was a circle. This is also a circle, but it's not obvious. And so we'll go through the steps to determine that it is a circle in this fashion. We're going to convert to a rectangular equation, so we have to get either r squareds or r sine theta or r cosine theta, and we actually did something like this previously, I think. We can't square both sides in this case because that's not going to help us on the right side. It'll get worse. We'll have 16 sine squared theta. On the left we'd have r squared, but it's not helping us overall. But if we multiply both sides by r, then that creates an r squared on the left, and it creates an r sine theta on the right. And the significance there, of course, is r sine theta can be replaced with a y. And our squared theta can be replaced with an x squared plus y squared. And so now our equation on the left is x squared plus y squared equal our 4, and our sine theta is y, so 4y. Now, and I think we mentioned before that this is actually the equation of a circle that we might not recognize immediately, but what we can do here, as you see, is that we can subtract this 4y on both sides and then perform the process of completing the square on this left side. Okay, so what I'm going to, and to complete the square, whoops, I don't know what's happened here. Okay, to complete the square on y squared minus 4y, we take the coefficient of the y, -4, and we divide that by 2, so we get -2. And then we square, whoops, I'm sorry, I'm getting out of hand here. Then we square that -2, which gives us a +4, and so that's what we need to add to these two terms, so we've completed the square. But if we add 4 on the left side, we've got to add 4 on the right. On the left side, of course, when we factor this trinomial, that's the whole purpose, that when we factor this trinomial, it's a binomial square. That is, it's a perfect square trinomial. It's y minus 2 times y minus 2. And now when we look at this, we recognize, oh, well, this is a circle. And the x-coordinate of the center is 0, and the y-coordinate of the center is 2, and the radius is whatever we square to get 4, because this represents radius squared, doesn't it? So the radius is 2. So 0 for x, 2 for y, here's the center, and the radius is 2, so the distance from the center back to the origin is 2 as well, and that's the reason it goes to the origin. Here's the center, the radius is 2, so no matter what direction we go, we're going 2 units. So that's what this circle looks like. Now, we want to spend more time about these circles and maybe not have to go through all this process each time. It'd be nice to recognize the circle, how we could tell where the center is and how we can tell its orientation. But before we do that, we'll have a video clip that talks through about how to determine symmetry of a polar equation. And notice here the idea of symmetry. If we can imagine the y-axis going through here, okay, this circle is symmetric about that y-axis. That is, if we folded along the y-axis, the two sides would meet, wouldn't they? So the y-axis is like a mirror. And so we say this is symmetric about the y-axis, and that's useful if we would have known that in advance along with where the center is. So that's what we'll do on the next video clip.